Okay, so this is the questions we get for the assignment. A 30 centimeter long, 3 millimeter diameter nickel-plated horizontal wire is submerged and electrically heated to boil 1 liter of water at atmospheric pressure. It is assumed that the emissivity of the wire used is 0.5. So first, we need to point out the information, which is the long of the plate is 20 centimeter. The diameter is 3 millimeter, and the emissivity is 0.5. The diameter we need to convert into meter, which is divided by 1000, so it will become 0.003, and the length will give value of 0.03 meter. Then we read the question first. Critical nuclear heat flux and wire temperature that can be attained. So first, critical nuclear heat flux, which the equation we can get from the equation 10-3 from the textbook, which is this one, which is the length of the nickel plate is 30 centimeter, the diameter is 3 millimeter, and the emissivity is 0.5. The unit we need to convert to meter, which is the length will be 0.3 meter, the diameter will be 0.003 meter. So this is the equations for heat transfer of critical or maximum, equation 10.3, and we need to substitute all the information here from the properties, which is, we know first you need to have assumption. First one is a steady operating condition. Second is a heat loss from boiler is negligible. And the third is we need to use the saturation temperature 100 degrees Celsius to find the properties and the surface tension. From 100 degrees Celsius, we know the surface tension is 0.0589 Newton per meter. So this is the properties from the T saturation 100 degrees Celsius. This information you need to insert in the equation 10.3. So to find the CCR, which is the value of the coefficients from the table 10.4, we assume this questions is a small horizontal cylinder because the long of the nickel plate is only 30 degrees Celsius. We assume the nickel plate is a small horizontal cylinder because the length of the nickel plate is 30 centimeter, not in a meter. So the equation we need to use is 0.12 L star negative to the power of negative 0.25, and the L value need to be in this range. To find the L star, okay, then we substitute the information for gravity and the density and the surface tension inside this equation to find the L star. So here we know the value, we substitute and calculate the value, which is to be 0.5989, and the value is in the range 0.15 and 1.2. After we get the value of L, which is 0.5989 from this equation, substitute inside this one and calculate again. So the value will be this one, 0.1364 for the CCR, which is the value of the coefficients. And we substitute this value inside the equations of maximum heat transfer in this one. Okay. Okay, so all the informations is already have, and we just only need to substitute it inside the equations. So we substitute one by one like this, and we calculate it to get the final answer, which is 1.156 to the power of 6 watt per meter square. Okay, so next in this questions also wants us to determine the wire temperature that can be attained. So the equations will be used is the heat transfer of nuclide by Rosenau. This one, the equations. Why we use the heat transfer of nuclide? Because the critical or maximum heat transfer is in the nuclide pool boiling. Okay, then we continue to find the temperature of surface. This one. So we can substitute the value heat transfer nuclide by the value of heat transfer of maximum we just obtained before, which is 1.1, which is 1.156 to the power of 6 inside the equations like this. We substitute the value for Q max, which is to be 1.156 to the power of 6 in these equations, and all the informations we substitute to find the T surface. Then we will calculate and rearrange the equations to find the temperature of surface, and we will get the final answer is 120.06 degrees Celsius. Okay, then we already know the answer of temperature surface is 120.06 degrees Celsius. So we find the temperature excess by calculating the T surface minus T saturations. 120.06 degrees Celsius minus 100 degrees Celsius will be 20.06 degrees Celsius. So this temperature excess proof in the nuclear pool boiling region is in the range in the graph.
For question 2, the question asks to find the increase in temperature. Okay, for this question, we need to find Q film, Q radiation, and the summation of both Q. So, first, we are going to find Q film by using this equation. Most of the constant in this equation are found from table, which is this. For C film, it is a constant for horizontal cylinder, which is the value for C film is 0.62, and the other constant. After that, we substitute the value into the equation, and when we calculate, we get 30,317.19 watt per meter square. Next, we need to find the Q radiation, and the equation as shown here. So, the same as the previous one, we find the constant value from the table, then we plug in the value into the equation. We get 1033 megawatt per meter square. Lastly, we total up the Q, which the equation is Q total is equal to Q film plus Q radiation. We sum up their values and we get 133.03 megawatt per meter square. This concludes that the increase in the wire temperature is 133.07 megawatt per meter square. For question C, we need to find the time taken to raise the temperature of cold water from 14 degrees Celsius to the boiling T, which is 100 degrees Celsius. So first step is we need to find the energy needed using this equation. Q is equal to mCp delta T. Here is the list for the equation. Rho, which mean density, area, height is equal to the length of the plate, delta T and Cp. Then we need to find the mass equal to rho times area times height, and the result is 2.12 to the power negative 6 joule. So by using this equation, it equal to m times Cp times delta T, and the answer is 1.173 joule. Okay. After we found the value, we use this equation to find the time taken to raise the temperature, which Q is equal to KL times area times delta T times T over D. For this equation, the constant, the value used is shown here, where D represent the length of the plate is equal to 0.3 meter. From this equation, we organize the equation as T the object, and it yields to T is equal to QD as QD over KL area times delta T. Then we substitute this value into the equation, and we find that T is equal to 250.11 seconds, and it's similar to 4 minutes 17 seconds. Thus, from this value, we know that we need 4 minutes 17 seconds to raise the temperature of the cold water from 14 degrees Celsius to the boiling T, which is 100 degrees Celsius.
For question B, the calculation is actually similar with question A, but as the pressure decreases, the properties might change. For question B1, we have to calculate the critical heat flux for the nuclide. In order to get the Qmax, we have to use this equation 10.3, which is actually the same as equation that we used in question A1. But in this situation, we have to choose the properties correctly, which is in between 71 kPa until less than 1 atm. Substitute all the values into the equation, and what we get is this. This answer shows that the Qmax has increased. Qmax increase as the pressure decrease. To find the temperature of the wire, we are still using the same equation that we used in equation A, which is this equation. Then we substitute all the values from the properties that we choose, which is 70.14 kPa and T set. It is actually T set equal to 90. Therefore, the temperature of the wire is 109.70 degrees Celsius. For question B2, we have to find the increase in the wire temperature. It is the same way as we done in question A, but bear in mind the pressure right now is 70.14 kPa. All of the properties is under 70.14 kPa condition. For this equation, we have to convert the T wire and T saturation into Kelvin, which is plus by 273, and it will change into Kelvin. In order to find the increase in the wire temperature, we have to make sure we have to consider the Q rate. Q total is equal to Q film plus Q radiation. Therefore, we have to find the value of Q film first, then Q radiation. After we sum up both Q film and Q radiation, what we get is this value. As we can see, the Q total for the lower pressure is higher, but for 1 atm, the Q total is lower. For question B3, we have to find the time taken to raise the temperature of water from 14 degrees Celsius to boiling temperature. So, in order to get the time taken, we have to find the equation that relate the temperature and time taken and heat flux. For this equation, it is the same as question A, but we have to change the temperature into Kelvin, which is plus by 273.15. It is found that the time taken is slightly increased, which is only 1 second. From this answer, we can say that the pressure does not affect the time taken to raise the temperature of water from certain degrees Celsius to boiling temperature.
Hi everyone, for the next question would be, what is the several recommendation that can be done in order to improve the performance of current boiling heat transfer system? There are 3 recommendations that can be done. First is to make sure that the liquid is pure liquid. This is because the boiling heat transfer coefficient of the liquid mixture is less in compared to pure liquid. This is because when it is a multi-component solution, the light component will evaporate first, and then the micro layer enriches in heavy component, which will cause the boiling point of the micro layer liquid to be increased Consequently, the boiling heat transfer coefficient would be reduced in comparison with the pure water or pure liquid. Okay, the second recommendation is use liquid or solution with low viscosity. In mixture, the viscosity is high, which had caused the heat transfer coefficient to be lowered. Hence, we can say that viscosity is one of the main reasons causing the large heat transfer reduction in DEA water binary solution. Hence, we can conclude that by using liquid or solution with a low viscosity, we can increase the boiling heat transfer coefficient. And last but not least is the bubble behavior. With larger bubble detachment diameter and also higher bubble frequency, the heat transfer coefficient tend to be increased. This is because the bubble behavior are dependent on the heat flux in nucleate boiling of mixture.
Question 3D. Explain how you can relate your investigation to real chemical industrial application. So, the answer for this question is the industrial of power electronic. Power electronic is the study of switching electronic circuit in order to control the flow of electrical energy. Power electronic is the technology behind switching power supplies, power converter, power inverter, motor drivers, and motor soft starter. Since the end of the last century, we have serious problem with the natural environment, energy resources, and global warming. In particular, the reduction of carbon dioxide emission is an important problem to be resolved urgently. In order to reduce carbon dioxide emission and save fossil fuels, the development of electric vehicles (EV) has recently been accelerated. In the EV power control system, an IC package is employed for electronic power equipment such as an inverter. The IC inverter produces large amount of heat and the maximum heat flux has been predicted at higher than 300 watt per centimeter cube. Boiling heat transfer is well known as a superior heat transfer technology to remove large amount of heat from a hot body using the transport of latent heat with a phase change. However, there are some difficulties with applying this cooling method to electronic. This heating surface become covered with coalescing bubbles at the critical heat flux. The maximum of nuclear boiling where the liquid is not fully in contact with the heating surface. So this is the diagram that involved in the power electronic industrial. The remaining liquid layer here or micro layer below the coalescing bubbles around here evaporates rapidly and the surface begins to dry. The boiling then turns rapidly to film boiling with the instant temperature rising through the transition boiling. Finally, the surface is seriously damaged by the high temperature. Finally, the surface is seriously damaged by the high temperature burnout. That will be takes place here. Generally, it is impossible to control the transition boiling, so it has been difficult to apply boiling heat transfer to the cooling technology in electronics. Bubble behaviors in subcooled pool boiling are shown here as typical example. A copper heating surface 10 mm in diameter is placed facing upwards on the bottom of the boiling vessel. The surface then is polished with the 500 sandpaper. The boiling liquid is a mixture of water and aqueous solution of 10% ethanol
this one, and 7.5% weight percent of propanol. The boiling is performed in subcooled coercive pool boiling under atmospheric condition. Large coalescing bubbles form on the heating surface on CHF collapse to many fine bubbles at the beginning of transition boiling. The liquid is supplied to the heating surface as the bubble collapse. The supplied liquid then evaporates and boiling bubbles again expand to large coalescing bubbles at CHF. The process is repeated rapidly and the heat flux exceeds the critical heat flux.